we now come to the first law of thermodynamics. And one of the things we need to address is a pesky minus sign issue that will come up. Now, um, various textbooks will handle this minus sign differently. Okay. So it depends on the convention of how you want to define the work as to how to handle the minus sign. Now, the OpenStax textbook will tell you that the work done is equal to the integral of p as a function of v dv. Okay, I'm going to claim that my convention, which is the convention of other standard textbooks, it's really split 50-50 how you handle this. Okay, um, my personal convention that I prefer is this one. So I'm going to define work like this. Okay. So I'm going to say that work is equal to the negative of this integral of p as a function of v dv. And we'll see how this operates here in just a moment. Okay, now, first things first, if you notice, in our previous example from the last video, um, the work that we calculated when we compressed the gas, when an external agent went and compressed the gas, we got a negative amount of work. I'm going to now say that that work is positive. Okay, so if we put this minus sign out front, then our work becomes positive. So the sign convention that I'm going to follow for this lecture is using this equation, work is equal to the negative of the integral p dv. If the result of that calculation is positive, then this means that work is done on the system by the environment or some sort of external agent. Okay? And when this work is positive, this increases the internal energy of the system. Okay? So when you compress a gas, let's say you have a gas in a container and it has a movable piston, and I compress that gas, all else being equal, if that's the only process that's happening, then I'm going to increase the pressure. I'm decreasing the volume and I'm increasing the pressure, and that will cause an increase in the internal energy. It will cause an increase in the agitation of the molecules. They have a smaller amount of space to move around in, and because I'm not changing the amount of molecules, that means there's less space for an individual molecule with which to move before it collides and so forth. Okay, so the total internal energy of the system is going to increase. If the result of this calculation is negative, then the work done, this is work done by the system on the environment. So this would be like the gas itself expanding the piston. Okay. So when this happens, this decreases the internal energy of your system. Okay. So this is the sign convention moving forward that I'm going to use. Other textbooks, the ones that use this equation, will have exactly the opposite sign conventions. So if you use the top equation for work there, then when work is positive, that means that it's work done by the system on the environment, and if it's negative, then that means it's work done on the system by the environment. Okay, but to me, the way it makes sense in my head to kind of start the process of thinking through whether something is positive or negative, it makes sense to me that work done by the environment would cause an increase in the internal energy of the system. So that's why I prefer this calculation to be positive under that condition. Um, and so, that being said, the general idea behind the first law of thermodynamics is that in general, there are two processes that will change the internal energy of a thermodynamic system. Okay? Number one, we've already discussed, which is work, and the other is heat, whether that heat is added or removed. And usually that is done via some sort of thermal bath, some sort of thermal reservoir. Okay? You can think of putting something on the stove if you have a thermally conducting uh, boundary, okay? Or you can put it, say, in the freezer, right? And in both of those cases, you will either be adding heat to the system or taking heat out of the system, all right? So these are the two processes by which the internal energy of a thermodynamic system will change or can change. Okay. And so this brings us directly to the first law of thermodynamics, which says, okay, the first law of thermodynamics says the increase, or not increase, but change, it can be either positive or negative. The change in internal energy is equal to the heat that is added to or subtracted from the system plus the work that's done. If the work is positive, then delta int will tend to increase, and if work is negative, then that will tend to decrease your internal energy. So what happens is Q can be positive or negative, and work can be positive or negative. So the resulting change in internal energy will be whichever one has a larger magnitude and in that direction. Okay, so I can let the system do work on the environment and take energy out of the system while I'm also inputting thermal energy into the system. And in that case, it will just depend on which amount of energy is larger, the energy that was lost or the energy that was gained, as to whether the total change in your internal energy will be positive or negative. Okay? So, the amount of heat that your system exchanges with the environment plus the work that's done will be your total change in internal energy. Okay? So, this is the first law of thermodynamics. Um, some common thermodynamic processes. Okay? How is this energy changed? Or how is this internal energy affected by certain processes? Okay, now these are not the only thermodynamic processes, but these are the most common. Okay, so you have isovolumetric, and isovolumetric means your volume remains constant. Now, if your volume remains constant, you don't have any dV. And since work is equal to the integral of P dV, if dV equals 0, then the work done equals 0. So there's no work done by the system on the environment or vice versa, right? So in that case, the second law of thermodynamics reduces to simply heat transfer. Okay, if heat is gained or lost, then that will be equivalent to your change in internal energy. Okay, number two, isobaric. This is constant pressure. So if your pressure is constant, okay, um, if your pressure is constant, then the work done, your pressure can come out of the integral, and this just becomes negative P delta V, evaluated from V1 to V2. right? Um, and so your law still reads E int, delta E int rather, is equal to Q plus negative P V2 minus V1. So if you compress your gas, then V2 is smaller than V1 and your result is positive once again. And again, compressions in R sign convention go to increasing the total internal energy. And expansions would go into decreasing the total internal energy. Then we have isothermal. Okay, so isothermal means constant temperature, and since your internal energy um, depends on your temperature, that means that if you have an isothermal process, then you don't have any change in internal energy. So, with that in mind, what that means is that if delta int, delta E int is 0, then that means that your heat and your work done must be opposite of one another. Okay? So in this case, I gain as much energy and heat that I lose through work, or I lose as much energy through heat that I gain from work. So in your isothermal process, you have to be in thermal contact with some sort of thermal reservoir. Okay? You have to be able to exchange heat with your environment. Okay? Um, and the fourth is your adiabatic process. And this is exactly the opposite, right? In your isothermal, you must be connected to a thermal reservoir. And in an adiabatic process, you are completely isolated from thermal reservoirs, and therefore no energy is exchanged by heat. And that means that Q equals 0 for an adiabatic process. Okay? And that means that your change in internal energy is equal to your work. Okay? So all of these are very common processes in various systems. All right. Now, again, these are some of your simpler general processes, but they are not the only processes. Okay. But they do happen quite frequently. All right. So, with that in mind, the entire drive behind the first law is eventually to calculate delta E int. Okay, that is the major function of the first law. Okay, and we want to know. Well, the reason we want to know is because your change in internal energy tells you something about the microscopic properties of your system. Okay, so remember that heat and work, things that you can measure with thermometers and energy meters, should you have some sort of energy meter, um, and so forth, are macroscopic properties. Okay, your pressure and your volume, things that you can measure with a pressure gauge and a ruler. Um, those are macroscopic properties, but your internal energy gives you some snapshot of the average state of an individual particle. Okay, so that's one of the reasons why the first law is powerful and why it is useful. Okay, if I want to say something about the individual properties of the individual particles, then your first law is the way to go, right? So, without further ado, let's check out an example here, okay? So we have an ideal gas that's compressed at a constant pressure of 1 atmosphere from 9 times 10 to the negative third meters cubed to 2 times 10 to the negative third meters cubed. And in the process, the gas absorbs 1,000 joules of energy in the form of heat. So we want to know what the change in the internal energy of the system is. Okay. So kind of going back to a problem-solving recipe, I'm going to write out what our givens are. Okay. So even though this is like one of the last pieces of information in the problem, I'm going to start with this one because it's one of the easiest to interpret. Okay. So this sentence, in the process, the gas absorbs 1,000 joules of energy in the form of heat. So that means that Q is equal to 1,000 joules, and that is positive. Okay, and I'm actually going to put a period here, so this is exactly 1,000, and therefore we have 4 significant figures. Okay, so my heat that's gained is 1,000 joules. So because the system absorbed that heat, it goes into increasing the internal energy. And then we also have our pressure, our initial pressure at 1 atmosphere. Pascals, right? And our initial volume is 9 milliliters, or not 9 milliliters, but 9 cubic meters is really how it should be said. And our final volume is 2 millicubic meters. And that's all we're given, right? But we are told, okay, there's another piece of information that we need that's not going to go into our givens as a variable or as a given quantity as an algebraic expression, but we are told this is an ideal gas. So that tells us that our pressure can be written as NKBT over V. Okay. So what to do? But we're told one other piece of information that actually simplifies the calculation, and that is that we are at constant pressure. So, constant pressure, coming back to our 4 common processes here, this is isobaric, and therefore the work done is equal to negative P delta V. Okay? So, what this means is we start with the first law of thermodynamics, and we already know our Q, that's going to be 1,000 joules, so we have to calculate work. And since this is isobaric, this is going to be negative P times V2 minus V1. So this is negative 1.01 times 10 to the fifth pascals, times 2.0 times 10 to the negative third uh, cubic meters minus 9 times 10 to the negative third cubic meters. Okay. And when we do this calculation, we're going to get, I'm going to start with the cubic meter subtraction. So 2 times 10 to the negative, well, obviously it's negative 7 times 10 to the negative third, right? So this is 7 times 10 to the negative third with a negative sign times 1.01 times 10 to the fifth. Okay, so that gives us negative 707. And then that multiplied by the negative sign out front gives us 707. Okay, so 707 joules is done by the work acting on the gas. So again, this is positive because the gas is being compressed. So some sort of external agent has to be doing the work. And therefore, our change in internal energy is going to be the heat that's absorbed plus our work done from the isobaric process. Okay, and so this is going to be 1707, which rounds to 1710 to three significant figures. Okay, so our change in internal energy was 1710 joules, and this went into increasing the internal energy. Okay, but your processes don't always have to do that. Okay, your processes can certainly decrease the internal energy, especially if you're letting the gas do some expanding while you are putting energy into it through heat. But in any case, okay, so this particular situation is like putting a gas on a stove, if you will, like a container that's thermally conductive on a stove. So you're adding heat while you're simultaneously compressing some sort of piston. Okay, so you're both adding heat and you're compressing the system, and both of those processes are going to increase your internal energy. So a second example, we have a monatomic gas, and it's expanding isothermally from 250 or 0.250 cubic meters to 0.750 cubic meters at a constant temperature of 700 K. And if the initial pressure is 1.5 times 10 to the fifth pascals, we want to A, find the work done on the gas, B, the thermal energy transfer, and B, the change, or C, the change in internal energy, right? So once again, kind of writing out our givens here, okay? So number one, we know that this is an isothermal process, right? So our temperature is constant at 700 Kelvin. We know that our pressure, and this is the initial pressure, is 1.5 times 10 to the fifth pascals. And we know our volumes. Okay, now before going any further, I would invite you to come back and consult this table. Okay, so isothermal, meaning the change in internal energy is zero, because remember, your change in internal energy, um, got to go back and remember the formula. So remember, E int is 3 halves NKBT. Okay. And so if there's no change in temperature, right? Because if I take the change in this, and actually let me do it this way. So this is relating the isothermal process. N times KB times T. So if I take the change, then this becomes 3 halves NKB delta T. And so if delta T is 0 for your isothermal process, then delta E into 0. So this is where the justification for this statement comes from. Okay, this is the justification for this statement. And so what that means is Q and work are going to be negatives of each other. All right. So what we can see here under our sign convention is that since the system is expanding, our work will be negative. Okay? Our work will be negative, and therefore our Q will be positive. All right? So basically what we need to do is find the amount of work that's done. If we solve part A, then we know B and we know C automatically from the condition of isothermal processes. Okay, so I guess what I'm saying is you can actually immediately state what the answer to C is. Your change in internal energy is 0, and then once you solve A, you know the answer to B. Okay, so let's solve A. The work done, since this is an ideal gas, once again, our pressure as a function of volume is going to be NKBT over V, right? Our work done is therefore going to be negative the integral of V1 to V2 of NKBT over V dV. But we don't know how many atoms there are in this gas, right? So we don't know N. So we need to find N, all right? So we can get this from the ideal gas law because we know that Pi times Vi divided by T has to equal NKB. So I'm actually going to group these together as a constant and get their product together, okay? So plugging in these numbers, we know that Pi is 1.5 times 10 to the fifth pascals times zero point 0.2 cubic meters divided by our temperature of 700 Kelvin, right? And so this is going to be 1.5 times 10 to the fifth times 0.25 divided by 700. And so N times KB is going to be 53.57. Okay? And the units are going to be the units of KB. So this is joules per Kelvin. All right. Okay, so that allows us to actually perform this integration, right? And really, we actually could have multiplied our temperature through there because it's isothermal, so it's constant. So technically, the entire numerator comes out, but that's okay. We'll just throw in that calculation when we need to. Okay. So we've already done this integral a couple of times, or at least once anyway. So this is negative nkb times t times the natural log of v2 over v1. Okay. And so this is going to be negative 53.57 joules per Kelvin times 700 Kelvin times the natural log of 0.75 over 0.2, but that's the natural log of 3, right? So 0.75 over 0.25 equals 3. So this is the natural log of 3. So if I take 53.57 times 700 times the natural log of 3, we get negative 'Okay, so the three significant figures, negative 41,200 joules. All right, so that was the work done. Pardon me, that was the work done. And since the gas worked to expand the container, our work is negative because it's doing work on the environment. So as a result, that means if this is going to be an isothermal process, if my temperature can't drop, that means I had to absorb that same amount of energy to keep the temperature the same while this process was happening. So my temperature, or my heat, therefore, uh, 41,200. Can't draw today. There we go. So the system did 41,200 joules worth of work on the environment, or negative joules of work, and therefore it had to absorb 41,200 joules of heat to allow the temperature to stay constant. But because the temperature stayed constant, your change in internal energy is 0. Okay? So there are a couple examples of how to use the first law in practice. And up next is the second law of thermodynamics.